First recording. Check. Good. Okay. Nice. So we've got just a couple of things to tidy up. And so I'm not going to do review because we finished a hypothesis testing question, and I've got another one later in the slides. And so we'll use that for our kind of review, I guess, later. But I did finish, and I had to rewatch my own video this morning to figure out, well, what did I say? And then I think I know I finished by saying, okay, we can do hypothesis testing with confidence intervals. And so they kind of merge like that. And so what that's going to look like, or what that could look like, is I'll make a note here. This is section 5.3 continued. Continued from last day. Just kind of covering all our bases for inference. And so to join the two, hypothesis testing and confidence intervals, right? If we have a confidence interval, right, then, so earlier we calculated a 95% confidence interval. This was last week, so kind of a long time ago. For the proportion of American Facebook users who think Facebook categorizes their interests accurately as 64 to 67%. And so we have a confidence interval of 64 to 67%. Or I guess I could say, I'll do it as proportions, 0.64 up to 0.67. That's from my confidence interval calculation, and we did that last week. Based on this confidence interval, do the data support the hypothesis that I'll say a majority of American Facebook users think Facebook categorizes their interests accurately? And so now we have this hypothesis, which means that we need to state our null and alternative hypotheses. Here's one that, so a majority, it comes up quite often in the assignment questions. And I always get questions, well, it just says a majority. What does that mean? And if you took a step back and you kind of think about it, what does a majority mean? A majority means more than 50%, right? And so more than 50%. So it does give you a number just kind of implicitly in this one scenario, right? This is the only time really where it doesn't give you the P naught, right? This is going to kind of evolve into our P naught in our hypotheses, right? But it's implied, right? I can't think of any other scenarios, right, where it's implied. So if we set up our null hypothesis is that P is equal to 0.5, right? Or in words, which you're allowed to do. So I always do my hypotheses with the parameter and the number because I'm going to need that number later, right? But if you prefer to write it out in words, that's totally fine. Okay. And so 50% of American Facebook users think Facebook categorizes their interests accurately versus the alternative hypothesis that P is greater than 0.5, right? More than 0.5. So this means that our alternative hypothesis is that P is greater than 0.5. Right? That's where that came from. More than 50% of American Facebook users think Facebook categorizes their interests accurately. Now, when I ask you to use a confidence interval to test a hypothesis, you will need to state your null and alternative hypotheses still, but usually the easiest way to kind of test it, or check it rather, is if you draw a number line, and maybe I'll do P is between 0 and 1, right? So proportions are between 0 and 1, and we have our hypothesized value of 0.50. We also have our confidence interval between 0.64 and 0.67. And so on this number line, it helps if you kind of draw out your confidence interval. Now, the lowest value is here at 0.64 and somewhere here, 0.67. It doesn't need to be to scale. You're just kind of visualizing what's happening. Yeah. Now, if I zoom in here, this confidence interval, right? How we interpret the confidence interval is I'm 95% confident that the true proportion of American Facebook users who think blah, 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 blah is somewhere between 0.64 and 0.67, right? But that also could translate to, well, I'm 95% confident that it's not 0.5, right? 0.5 is outside the interval, right? And so here, the null value is not included in the interval, right? And so, right, P is equal to 0.50 is not included in the interval, which means we're going to reject the null hypothesis. Okay? And so, whereas if the interval includes the null value, right, this null hypothesized value, then that is one of the options that we're okay with, right? And so then we would not have enough evidence to reject H naught. I'll highlight this, but I always find that kind of drawing the number line is pretty helpful, right? Because then you can see it. Oh, well, no, I'm 95% confident that the true proportion is somewhere in here. Therefore, I'm 95% confident that 0.5 is not one of those options. This is a quick and dirty, I love that she included it in the slide. This is a quick and dirty approach. And so it is kind of where we're heading, because p-values are kind of tricky sometimes. But for now, most scientific articles and things like that use the p-value, which we learned a lot about last day and the day before, and we'll see again today. And so, but we can use a confidence interval to test a hypothesis, right? Especially if we have just a quick hypothesis and we've already built a confidence interval, right? And so on a test, it's pretty reasonable for me to ask you to construct a 95% confidence interval or 90% confidence interval, whatever, for something. And then a follow-up question would be, based on this confidence interval, right? What do you think about this hypothesis, right? Sometimes, even though I only give you like this much space on the page to do it, sometimes people think I need to do a full-blown hypothesis test here. You don't have, I'm not going to deduct marks for that because it's technically correct, but it will say based on this confidence interval. So then you're allowed to just use this confidence interval like that. The problem is it doesn't tell us the likelihood of the certain outcomes, so it doesn't give us a p-value. But sometimes it is valuable to know the range of plausible values. Okay, so we spent a lot of time on our conclusions last day, right? We only have two options. I either have enough evidence to reject H naught or I don't. Okay? There's always a chance that we're wrong. Right? And so that brings us to decision errors. So hypothesis tests are not flawless, right? There's always a chance. There is always, I'll say, a probability we are wrong. So in a court analogy here, in the court system, innocent people are sometimes wrongly convicted. We understand that. And the guilty sometimes walk free. And so those would be kind of the equivalents to the decision errors that we could make. And so we can make a wrong decision in statistical hypothesis tests as well. And so we're going to have tools and kind of probabilities, and we already saw how the alpha level behaves and makes it harder to reject H naught if we make it smaller, right? So that's one of the tools that we have. I will make a note here in red, so it's important. Since there is always a chance our conclusion is wrong. Now, we don't know if it's right or wrong. We'll never know, right? That's the reason we never accept a hypothesis. We can never accept a hypothesis. Okay. I will take marks off. Rude. But now I've said it. I will take. Okay. So you never use the word accept, right? I accept H naught. No, you don't. You fail to reject H naught. So what are these decision errors? I think the simplest way to summarize it is in this table. Okay. And so we have our two competing hypotheses, the null and the alternative hypothesis, right? And so in our population, which we'll never know about, right? But there is some truth, right? So if we actually surveyed every American Facebook user and asked them this question and all of them answered, you can see how that's kind of a problem, then we would have the population proportion, right? So there is some true value that we're trying to figure out what it is through sampling. Okay. And so either H naught is true or HA is true, but we don't know which one is true and which one is false. But if the null hypothesis is true, okay, then if you fail to reject H naught, right, that's fine, that's good, right? You don't have enough evidence to reject H naught is true, that's fine, right? That's a good decision. If H naught is true, but you reject H naught, that's what we call a type 1 error. And so when we reject H naught, it's possible that we're making a type 1 error. Because our p-value, remember, is the probability that that we saw a p as extreme or more extreme, assuming the null hypothesis is true. Now, it could have just happened by random chance alone, right? But if it's small enough, if that probability is small enough, then we reject H naught, but then we open ourselves up to a type 1 error. So I just want to highlight here that if we reject H naught, we could be making a type 1 error. Whereas if we fail to reject H naught, when we should have rejected H naught, right? When HA is true now, then I'm making a type 2 error. But notice, depending on my decision, there's only one type of error that I could make, right? And so if I'm going to do a shorthand FTR, fail to reject H naught. We could be making a type 2 error. If HA is true, so if the alternative hypothesis is true and you've rejected H naught, then that's a good decision. So in words, if you don't like the table, in words, a type 1 error is rejecting the null hypothesis when H naught is true. And a type 2 error is failing to reject the null hypothesis when HA is true. I would say never, but she says almost never. There are scenarios where we could know everything about the population, but we almost never know if H naught or HA is true, but we need to consider all these options that, hey, I could be making a mistake. Before I spend time writing it out, fine, I'll add it here. Keep it all on this page and then we can kind of cruise through the easiest way to decrease the probability of making a type 1 error is to decrease your alpha level, right? Makes it harder to reject H naught. I need more room, I guess, if I'm gonna do this. Okay. To decrease the probability of making a type 1 error, we decrease the alpha level, right? That makes it harder to reject H naught. It just means that you need a lot of evidence against H naught before you go ahead and reject it. Make it harder to reject H naught. So we have a lot of control over our type 1 error rate. And before you go and conduct a study, usually one of the things that you should do is to set your alpha level before you've even seen any data, because otherwise it's so tempting to adjust it afterwards, right? But you need to set your alpha level, and usually it's 0.05, right? But if you want to make it really hard to reject H naught when you shouldn't, right, type 1 error, then you make it really small, 0.01, 0.001, right? Whereas the type 2 error rate, there's not a lot that we can do to decrease the probability of making a type 2 error, right? Type 2 error is when the alternative hypothesis is true, but I failed to reject H naught. Okay. Usually the problem is that I just don't have a big enough sample, right? And so then we need to increase our sample size. So this one, we're kind of helpless to decrease the probability of making a type 2 error. We one of the main ways is we can increase the sample size. What does increasing the sample size do? This is more of a side note, but the standard error of p hat, for example, is, let's say, p hat q hat over n. If I increase my sample size, then I'm dividing by a bigger number, right? And so then this overall thing in the square root becomes smaller. And if I take a square root of a smaller number, then the standard error, which is the spread, is going to decrease. It's going to tighten up, right? Which means that our estimates become more precise, right? We're more kind of sure of our p hats. That's extra, but if this increases, then this whole thing decreases, right? So then we decrease the spread around our p hat, right? And we get better estimates. Textbooks love using the trial scenario, right? So in a court system, if we think of a hypothesis test as a criminal trial, then we can frame the verdict in terms of the null and alternative hypotheses. So the null hypothesis can be that the defendant is innocent. We have to assume they're innocent until we are able to prove that they're guilty, right? We assume innocent until proven guilty, right? That's our null hypothesis. And that's what we do all the time, right? In our null hypothesis, we say, okay, if I want to prove that there's a majority, first I assume that it's at 50% until I have a lot of evidence against that. Which type of error is being committed in the fall, and then the alternative is, of course, that the defendant is guilty, right? But you don't want to jump to that conclusion until you have enough evidence against H naught, right? So which type of error is being committed in the following circumstances? Okay. And I think I have, yeah. Well, okay, fine. I'll just skip to the solutions here. Because these, I find you really need to kind of sit down and think about, right? But I'll just talk about why it's a type 2 and a type 1 error. So declaring the defendant innocent when they're actually guilty, in terms of our decision, right? Declaring the defendant innocent, that's failing to reject H naught when HA is true. So if you go back to that table, that's a type 2 error. Whereas declaring the defendant guilty, that's the same as rejecting H naught when they're actually innocent, when H naught is true. From here, which is a type 1 error, right? Anytime that you reject H naught, you could be making a type 1 error. And anytime you fail to reject H naught, you could be making a type 2 error. We don't know, but we need to recognize that. Now, there are scenarios where kind of the gravity of the errors that we could be making kind of change, right? A type 2 error could be worse than a type 1 error, but generally speaking, right, a type 1 error is worse, okay? So this is finding that someone, an innocent person is guilty, right? It tends to be worse, and you know, you can kind of go back and forth on this, than if someone's guilty and you let them walk free, right? Because it's way worse to send an innocent person to jail, right? At least that's the general consensus. And so, which I agree with, but open to interpretation. So better that 10 guilty persons escape than one innocent suffers, kind of the broad strokes. So the type 1 error rate comes from our alpha level. And so we reject H0 when the p-value is less than 0.05. So that means we use a significance level of 0.05, or alpha is 0.05. And so for those cases where H0 is actually true, we don't want to incorrectly reject it more than 5% of those times. Now, we don't know if we're in one of those times, right? And we'll never know. Okay? But 5% significance level or an alpha, right? This is the same as alpha equals 0.05. We're okay with making a type 1 error 5% of the time. And we don't know if we're in one of those 5%, right? But that's low enough for us to feel comfortable. Yeah. And so this is why we prefer small values of alpha, and increasing alpha increases the type 1 error rate. Nice. So those are decision errors. Any questions about those before we get into chapter 6? We're ready. Chapter 6, inference for categorical data. This is where the fun begins. Chapter 6, we talk about, okay, inference. Inference is, let's talk about what inference is. Inference is hypothesis testing and confidence intervals. It's an umbrella term for hypothesis testing and confidence intervals. Categorical data, right? From our two different types of variables, we can have a categorical variable or a numerical variable. And from a categorical variable, we analyze proportions, right? Counts out of sum total. And so what we're going to do as a roadmap in 6.1, we're going to do some examples of a one sample proportion type of question. And I know what you're thinking. Haven't we been doing that this whole time? We have, and we just get to do it again. Okay? I introduced one new-ish topic. I say ish because we could have solved it already, but we haven't talked about it explicitly. But 6.1 is one sample proportion. P. All right, our hypothesis and our confidence interval, we're trying to learn about what P is. In 6.2, we move up to two sample proportions. P1 minus P2, right? How do they compare? Now I have two proportions and I want to compare the two. 6.3, right? See a pattern yet? 1, 2, 3. It'll actually be 3 or more, so it just kind of takes it away, right? 3 plus sample proportions. P1, P2, oops. P3, etc. And then finally in 6.4, we consider if two categorical variables, right, are independent of each other. Two categorical variables to see if they are independent. So from here on out, we're going to do 6.1 today, and a lot of it, we've seen pretty much everything of it today or these past couple of weeks already. And then every day we introduce a new type, right? We talk about, okay, what does the null hypothesis look like? What does the test statistic look like? What does a confidence interval look like, right? And so for all of these scenarios. So 6.1, inference for a single proportion. And I guess I could say in chapter 7, we do the same thing, but for numerical data, right? Where we talk about means. We start with one sample mean, and then we go to two sample means. It's kind of two different ways that we could have two sample means. Stay tuned. And then 3 or more sample means. So there's that symmetry there. So for our example, so long, I'll read it to you. I'll do a shorthand version probably. Two scientists want to know if a certain drug is effective against high blood pressure. The first scientist wants to give the drug to 1,000 people with high blood pressure and see how many of them experience lower blood pressure levels. Hopefully already you're kind of like, oh, that's a weird way to collect that data, right? Don't you need a control group? So that's where the second scientist comes in. The second scientist wants to give the drug to 500 people with high blood pressure and not give the drug to another 500 people with high blood pressure, and see how many in both groups experience lower blood pressure levels. Which is the better way to test this drug? If you want to compare the two, right, I'd say you should have a treatment group and a control group, right? Because then you'll know if the difference, right, or the change is due to the treatment, right, or just by random chance alone. So here, the control group shows what would happen by random chance alone. There's been a lot of studies done, the placebo effect, right? Because here, if you have a drug and it might be, you know, some pill, right? And then you can give the control group a sugar pill and they think that they're getting this drug, and that can be very effective, right? Just thinking that you're getting this miracle drug is going to help you, right? And kind of a large amount of time, it does help. So who knows? The GSS is a social survey. So I think it's called a general social survey in the States that they do. And so it's just a broad survey from Americans. And so the GSS asks the same question. And so, hey, how would you conduct this study? And 99 out of 670 said that all 1,000 get the drug, right? Whereas 571 out of 670 said, how about we split it, right? Give it to 500 and 500 who don't, right? Both of these, we can generate proportions with each of these, right? This is our N, 670. And depending on what we want to talk about, right? That will determine if this is a success or if this is a success. Yeah. I will highlight it here because it gets a little bit confusing on the next slide, I'm pretty sure. And so we will think of this group as the people who have good intuition about experimental design. Pretty lofty, but as the group who have good intuition about experimental design. Just because that's the wording that she uses, although I think she has a typo somewhere making it sound weird, but basically that's it. And so in this scenario, my successes, my number of successes is 571, right? If I wanted to talk about, okay, what proportion of Americans have poor intuition about experimental design, then my successes would be this one, right? So depending on what I want to talk about, right, that determines what my X is. Okay. I think there was something else, but that's okay. We would like to estimate the proportion of all Americans who have good intuition about experimental design. That is, they would answer 500 get the drug and 500 don't. What are the parameter of interest and the point estimate? And so the thing that we're interested in is the parameter. The parameter is the proportion of all Americans who have good intuition about experimental design, right? They picked that correct option. And so P is a population proportion, right? And this is all review, right? But kind of being introduced as a whole in this section. So we have seen it in all of chapter 5 already, right? So if it's sounding familiar, that's why. But we're just doing a full run through. So we're trying to figure out what P is, right? The proportion of all Americans who have good intuition about experimental design. The point estimate, right, is the proportion of sampled Americans who have good intuition about experimental design. And what we found is, in general, P hat is X over N, and that's where, depending on what you want to talk about, that will determine what your X is. In this case, our X is 571 and our N is 670. My trusty calculator. 571 over 670. I get a P hat of 0.852. I think she rounds it to just 0.85. Or P hat is 0.85. Because I'm going to try to just use her notes, I'll do a little bit more here. She just does 2 decimal places. Fine. So now we have our sample proportion, and we're trying to learn, right, what the population proportion looks like. We suspect it's probably close to 85%. Right? There's no reason to expect our P hat to be much off of the population proportion. Right? But we need to attach a spread to it to know for sure, or with some confidence. So what percent of all Americans have good intuition about experimental design? We can answer this question using a confidence interval, which is always of the form a point estimate, that's our p hat in this case, plus minus the margin of error. And the reason we're introducing this now is for the final part on your formula sheet for the one sample proportion. And so the margin of error is, we've seen it before, right? We have our Z star, which we find on the t-table, times the standard error of p hat. Or from our formula sheet, we've already seen p hat plus minus Z star times the square root of p hat q hat over n. So this whole chunk is our margin of error, ME. We spent a lot of time talking about this already. And so from the central limit theorem, we know that the standard error of p hat is, ideally, if we know p, then it would be p times 1 minus p over n, square rooted, right? But for a confidence interval, I'll add it here. The standard error of p hat is the square root of p hat q hat over n. Because, well, q hat is 1 minus p hat, right? And so, right, ideally, if we know what p is, but we're trying to figure out what p is, so we don't, so then we use our next best thing. And in this case, our next best thing is our p hat, right? That's my point estimate for p. So that's my best guess at what it is. And so I replace my p's with p hats. We checked our conditions last week, or earlier last week, this week, okay? But talks about the central limit theorem here, but we've spent a lot of time there already. So what if we want to build a 95% confidence interval? So the GSS found that 571 out of 670, which will use 85% of Americans, answered the question on experimental design correctly. Estimate using a 95% confidence interval the proportion of all Americans who have good intuition about experimental design. All right. So we're ready to go through and do this confidence interval. Okay, we're going to build this confidence interval from start to finish, which includes checking our conditions. It does have the solutions on the next few slides, but let's do it properly. Okay. Conditions for a confidence interval. Because they're slightly different for a hypothesis test. And we did the comparison last day. So first is the independence condition. I'm not sure it said they were randomly sampled. Let me confirm. But just like last time, it's reasonable to assume that they were randomly sampled or at least are independent of each other, right? Because this is a big survey that they conduct and hopefully they're doing it properly, right? And so we're assuming they did it properly is what we're going to say. So here we assume the sample was randomly selected. It's also reasonable to say that 670 is less than 10% of all Americans. N equal to 670 is less than 10% of all Americans. Probably adults, but it just says Americans. These conditions are the same for a hypothesis test, right? So far, we've checked the conditions for both a confidence interval and a hypothesis test. It's the normality condition where they're just slightly different. Right? The normality or the sample size condition for a confidence interval, I need at least 10 observed successes and I need at least 10 observed failures. At least 10 observed successes, which, we have X is given to us as 571. Which is greater than or equal to 10. And we need at least 10 observed failures. If we talk about N minus X of my total of 670, if I take away 571, I seem to remember it was 99, right? Which you could also grab from your table, I'll confirm, but 670 minus 571, yeah. Which is also greater than or equal to 10. If you prefer, you could have still used N times P hat, 670 times 0.85, right? But because the 85% is rounded, you would get not a whole number. And in this case, we have X, so you may as well use it, right? But if you always want to use the same method, then you could use N times P hat and N times Q hat. But here, therefore, the conditions for inference are satisfied. Add a page. Okay. Now we're ready to build our confidence interval. Right? So from our formula sheet, let it be your guide. You've decided you have a one sample proportion question because I just have one sample. And one of the ways that probably the easiest way to pick between a proportion and a means question is for a means question, you have to have a standard deviation and we don't have any of that, right? I just have 571 out of 670, which is a proportion. So if I want to build a confidence interval, I go here because the question asked me to build a confidence interval. And before we can start, we can highlight all the information that we have, right? And so here, P hat is 0.85. We'll use what was given in the question. which means Q hat is 0.15, right? 1 minus 0.85. I'll show that work because that's still maybe not 100% clear yet, but it will be. And N is 670. And so we need Z star for, we were asked to build a 95% confidence interval. From the t-table, Z star is going to be 1.96. Right. Grab this. I want to build a 95% confidence interval and I need a Z star to do it. And so Z star is 1.960. Which is really just saying I need to move out 1.96 standard errors from my point estimate to make a 95% confidence interval. But now we have all the components and now we just need to build the interval. All right, that's phase one. So we've got p hat plus minus Z star times the square root of p hat q hat over n. We can plug in all our values, 0.85 plus minus 1.96 times the square root of 0.85 times 0.15 over 670. Then I can do my square root. A common mistake is you forget to do the square root, so let's make a mental note. Let's see here. 0.85 times 0.15 divided by 670. Take that square root. I'll check in here just so you can make sure you got the same number for the standard error. So my standard error is 0.01379. It keeps going, but let's end there. Usually I encourage you to keep all your decimal places. I don't know why I just lopped it off. I did. So this is the standard error of p hat. And did you guys get the same number? Because I feel like I flubbed it. Nice. Oh, I almost put it away. 1.96 times 0.01379. I get plus minus 0.0270284. So 0.85 plus minus that amount. This becomes our margin of error. Many research articles will report just the margin of error. Your point estimate, of course, and the margin of error. That's going to be your buffer. That's how I think of it. And if we build our interval, oh no. What if I do 0.85 minus that little guy? I get a lower bound of 0.8229716 up to 0.85 plus 0.0270284. 0.8770284. Or if we want to round it, let's do 3 decimal places. 0.823 up to 0.877. But wait, there's more. We have to interpret the interval. Right? It's only half the marks. It's just math, right? Can do it. So now, it's been a while since we interpreted an interval, but we use the same standard blurb, right? And so we are 95% confident the interval from 0.823 to 0.877. I like to get my numbers out of the way first, and then I can rephrase the parameter, right? We're 95% confident that the interval from here to here captures and I wonder if I use, or if not me, but captures. We were asked to estimate using a 95% confidence interval. What were we trying to estimate? The proportion of all Americans who have good intuition about experimental design. So that's what you take, the proportion of all Americans. It's important that you emphasize that it has to be about the population proportion, right? And so the proportion of all Americans let's see here. The captures the proportion of all Americans who have good intuition about experimental design, period. Not a question anymore. I snag the question for 2 reasons. One, I don't want to write it out. But 2, to emphasize that here, you're just going to take whatever I asked you in the question and just write it out. That's tedious, but it's not hard, right? Nice. And then we're done. This is the other half of the marks, right? All right. So the next few slides just kind of walk you through exactly what we just did. And so I will zip past those. But before we do that, here we had a margin of error of basically 0.027 or 2.7%, right? These are still, you can still work in percentages. What if your goal was to reduce that margin of error to 0.01 or 1%, right? Then you would need to adjust your sample size, right? The one way to do that would be to adjust your sample size, because you still want to make a 95% confidence interval, right? And you expect your p hat to be kind of close to the population proportion. And it also depends on n, right? But how we get a more precise estimate is by increasing our n, right? And so what we mean by that is, if you want to decrease the margin of error, right? Tighten up that buffer, then you need to increase n. And we'll have a calculation to do that. So let me just zip through, because we already did all of this together. Let me copy. I say that, but then I go back. We found, copy. Put it here. Put her there. We found our confidence interval was this, right? And so the margin of error, or we'll start calling it a lowercase m on your formula sheet. It's a lowercase m, just because to having two letters can be confusing, right? Are you solving for one thing or two things? All right. And so m in this case was 0.027 or 2.7%. How many people should you sample in order to cut the margin of error of a 95% confidence interval down to 1%? So now you want m to be 0.01, right? Down from 2.7 or 0.027. So if we think about what the margin of error is, and I've got a rogue p there. The margin of error m is the same as z star times the square root of p hat q hat over n. Now I'm going to show you how this thing came about, but before I do that, I will also show you that it is the last part on your formula sheet, is this sample size calculation. And so it's already been reworked for you. What's nice is one sample proportions are the only questions where we're going to be able to calculate the sample size. And so that's kind of nice, or that we will do it anyways. So if we want to solve for n, how many people, right, is really saying solve for n, right? Solve for n, that makes that happen. Okay, if I'm trying to get at n in here, I have a margin of error that I want to force, right? And so I'm going to force my margin of error to be 0.01. I'm still making a 95% confidence interval, and so z star is still 1.96. Right? We're going to assume that the p hat stays the same, right? Because we have an idea, and notice how over here, kind of spoiler alert, it's not really a p hat. We're going to have two options depending on the scenario. So p star, but for now, let's use 0.85 times 1 minus 0.85. Divided by n. I will highlight this and mention we assume p hat from the previous study holds. Right? That's not always the case. Sometimes or often you don't have a previous study that you could look at, right? You're going into this thing blind and you have to collect a sample size and you're trying to figure out, well, if I want to be able to report to a margin of error of 0.01 in my journal, right? Maybe some journals only accept if your margin of error is less than 2% or something like that, right? And so then you would need to figure out, okay, what sample size would I need? But this is my first scenario where we assume p hat holds from the previous study. So if we solve this, oh dang, maybe I shouldn't have put numbers in here. because I want to show that it devolves to this, or kind of evolves, I guess. Let me move that down there. See if I can do it in a couple of quick strokes. To solve for m, I would first divide, or sorry, to solve for n, I would first divide both sides by z star, right? Putting me at a square root of p hat q hat over n. To shake out that square root, I need to square both sides, which looks like this. M over z star squared is p hat q hat over n. Okay, I'll need a little bit more. And I started so big. Ugh. To solve for n, I think the easiest way to do it is to multiply this n over here, and then also divide the rest over here. So what I get is I get n times m over z star squared is p hat q hat. Solving for n, I get p hat q hat over m over z star squared. This is a fraction over a fraction, which means I can flip and multiply. And so this becomes, uh-oh, now I've really done it. This becomes n is z star over m all squared times p hat q hat. We won't always have a p hat from a previous study. In that case, we use 0.5, right? We assume a 50-50 split. Okay? And so we won't always have a p hat from a previous study. So we replace this. We replace p hat with p star. That doesn't look like a star. There. Which brings me here. From the previous. We're going to have two options for p hat, right? Either we use a previous study, or sorry, p star. We use p hat, or we use 0.5 if we have no prior information. So now, just moving this around. I really jumped the gun here on trying to solve it. That's okay. Soon enough, I'll get there. So we assume that the p hat from the previous study holds. And we could do this work with numbers just to emphasize it. Or if you want to jump right in and use the formula for n, you've already seen that that's how it's derived, right? And so that's okay. That's not part of the job, but it is pretty fun to do algebra. So 0.01 divided by 1.96 is the square root of 0.85 times 0.15. divided by n. And then I can square that. 0.01 divided by 1.96 is 0.85 times 0.15 divided by n. 0.01 divided by 1.96 is just a number. And so to solve for n, I'm going to multiply this over here and divide this over here. So I get n is 0.01 divided by, nope, opposite, 1.96 divided by 0.01 squared times 0.85 times 0.15. Once I do that, which is the same as just jumping in from here, right? Z star over m squared, p star to q star. 1.96 divided by 0.01, square that, times 0.85 times 0.15. I think I did something wrong. 1.96 divided by 0.01. Okay, there we go. Square that times 0.85 times 0.15. Okay, now I got it. I only got 48 earlier, so I knew I had missed a zero somewhere. But that's only because I know what it should look like. 4898.04. Now here's an important part. Even though 0.04 is small, and usually you would round down, when you're talking about a sample size, if you round down, right, then your margin of error is just going to be just a tiny bit bigger than you wanted it to be. So you're always going to round up. Okay. For n, we always round up. So we would need n equal to 4,899 people in our survey, which is kind of opposite to what you would naturally do with that rounding. But the idea is that, okay, if you need this many 0.04 people to get your margin of error to where you want it to be, then you should round up instead. Right? Nice, because your n has to be a whole number. Right? Any questions about that before I zip through exactly what we just did? So n should be at least 4,899 in order to get that margin of error. So like we said, nice. In our sample size calculation on our formula sheet, wait, what if there isn't a previous study, right? So then that's why I use a P star instead, okay? But if there isn't a previous study, bless you, then you're going to use a P star of 0.5. So here we have two options. Use P star is equal to, bless you, P hat, right? If we have a previous study, then we can use that P hat. Or P star is equal to 0.5, right? A 50-50 split. Okay. My hat got weird. Oh, sorry, it's a star, that's why. Well, it's still a weird star. I'll fix it. Still pretty weird. And the reason for that is twofold. If we don't know any better, then 50-50 is a reasonable guess, right? Why would you choose something other than 50-50? And then you can make adjustments as you go. Okay? But also, using 0.5 gives us the most conservative estimate. And so that's the best way to make sure that your sample size is really truly going to work. Okay? And so a lot of the time, I would just suggest that you would use 0.5 always for p-hat, even if you had a previous study. But what happens is it's expensive to collect a large sample size, right? It's great, it's good, but it can be expensive, right? And so what if we did the same calculation, but using p star as 0.5 instead? I know I'm going to get a bigger number, right? But let's see how much bigger. So we have our Z star over M squared times P star Q star. And in this scenario, now let P star be 0.5. So then I get 1.96 divided by 0.01 squared times 0.5 times 0.5.
What does the star even mean again?
It doesn't really mean anything. It's just kind of showing you that it's not necessarily p-hat and it's not necessarily 0.5. You have a choice.
Okay.
But that's confusing because that's not what the star means on the Z.
Yeah.
I know. They mean different things. If you want to use a p-hat here, that's cool. But it's a star on your formula sheet. So, and it's just to, so I put the star on your formula sheet to emphasize that you have two options.
Okay.
Right? And it'll say in the question, right? Assume you have no prior knowledge, or assume the results from last year still hold, or something like that.
Okay.
Yeah. 1.96 divided by 0.01, and then square that, and then times 0.5 times 0.5. I get a beautiful even sample size of 9,604 versus our previous sample size, which was 4,899. Nice, right? So when we had this kind of shift in the P's, right, and we knew that, then we were able to take a way smaller sample size, right? Imagine if you're offering $10 gift cards to every participant. All of a sudden, right, even at a $10 gift card, which is, you know, it happens all the time, 4,899 is a lot, but 9,604, that's way more money to be spending, right? And so it can be expensive because we need to coerce people to do our surveys usually. Or it's just hard to collect specimens if we're talking about animals and things like that. Okay. Nice. Sample size. Hey, look at us go. Wow. We already summarized the success failure condition, which I've been calling the normality condition. But it doesn't hurt to see it again. Yeah. So we did them side by side last day. But for a confidence interval, we need at least 10 observed successes and failures. And for a hypothesis test, we said we need at least 10 expected successes and failures, okay? Which means that we need, at least for a confidence interval, we need n times p hat greater than or equal to 10 and n times q hat greater than or equal to 10. Whereas for a hypothesis test, we need to rely on the null value, or the p naught. N times p naught has to be greater than or equal to 10, and n times q naught has to be greater than or equal to 10. I take clues from how the standard error is calculated, right? And kind of annoying, there's a typo on here that I fixed, but I'll do it with you. The standard error in the confidence interval, so the standard errors will always be the things under the square root. Okay? And so in the square root, we have p hat and q hat over n. Right? We use p hat, q hat over n. But q hat is just 1 minus p hat. Right, and so for a confidence interval, that's what we use to check our conditions. Whereas for a hypothesis test in the square root, we have a p naught, right, which is exactly what we use to check our conditions to do a hypothesis test. So I use that as clues for myself. So this is p naught, q naught over n. Nice. How about a hypothesis test? The GSS, we're using the same information, but now we're going to do a hypothesis test. We did a confidence interval, we calculated the sample size, and now we can do a hypothesis test. And if we're cruising around on our formula sheet, now we will have done all the things that we can do with a one sample proportion type of question. So hypothesis testing, here we go. The GSS found that 571 out of 670, or 85% of Americans, answered the question on experimental design correctly. Do these data provide convincing evidence? And that's my clue, right? That this is going to be a hypothesis test. That more than 80% of Americans have good intuition about experimental design. I don't think this, I think that's the typo I was thinking of. Okay. Step 0, check our conditions. Boring. How about I steal the conditions? Because we already checked or assumed that it was random. And so, and we already argued that 670 is less than 10% of the population. Where did we do that?
How many steps are there again in checking the conditions?
In checking the conditions, 2. Depends on how you want to break it down, because you have to check for independence and you have to check normality. Okay. But in independence, you have to make sure it was randomly sampled or assume it was. This one's optional.
If it doesn't say, then do we always assume that it was random?
Yeah. Yeah, totally. And then the normality condition has 2 parts, right? The successes and the failures. Yeah. So I'm going to snag this whole thing because it's going to be very similar, but I also want to highlight what the differences are. So now I'm going to do it for a hypothesis test. Right? These are the same as the confidence interval. It's just now the normality condition has changed, right? Which is the sample size condition. We need at least 10 expected successes, and I need at least 10 expected failures. So how we find that is, instead of this calculation, I need to do n times p naught, because it's a hypothesis test. Now that relies on us figuring out what p naught is from the question. Yeah. So for each of these numbers, let's go through and say, okay, this is my x, this is my n, p hat is 0.85. Right? And then P naught is going to be the number I want to compare my sample proportion to, right? Which is going to be this 0.8, right? I want to know if there is convincing evidence that more than 80%, right? 85 is more than 80%, but is it significantly more? So n times p naught is 670 times 0.80. So I'm expecting 670 times 0.8, 536, which is greater than or equal to 10. So that's great. I'm expecting 536 successes. Right? If the null hypothesis is true. And I can do the same thing, n times q naught, which is 670 times 0.2 is 134. So I'm expecting 134 failures if the null hypothesis is true. And therefore, the conditions for inference are satisfied. I've been calling this kind of step 0. I know.
For NQ 670 times 0.20 equals, what is it equal?
134, which is greater than or equal to 10. I tried to sneak it in there. How about this? I'll bump this over. Oh, I've written too crooked. I can't grab it very nicely. Oh well.
That's okay, I got it.
Nice. Now we're ready. So then the conditions for inference are satisfied. Now we're ready for our step 1. State the hypotheses. We had to do a lot of the main work, right, by figuring out what type of question we have, right, a one sample proportion type of question, okay, and to check the conditions, we already had to find P naught, and so a lot of that work has been done already. On our formula sheet, we have P is equal to P naught, right? That's our null hypothesis. But we need to replace that P naught with something from the question. So I'll erase that and change it to 0.80. Right? We have to assume that it's 80% or basically 80% until I have evidence against that. And what do I want to prove? I want to show that P is more than 80%. So I'm only concerned with that one extreme. So P is greater than 0.80. I tend to make a note here That this means I have a one-sided test, right? So later I'll need a one-sided p-value, right? Because I'm only concerned with one extreme. But it's optional, so I'll just do it in a lighter blue. This makes it a one-sided test, yeah.
Where did the 0.8 come from?
It came from here. The thing I want to compare my p-hat to, right? Nice. Okay. This is 2 marks. Because you establish a lot of what you're about to do in this part, right? You need to show me that you know that you're talking, that it's a statement, first of all, 2 statements, that you're talking about P, that you were able to pick the 0.8, that you have an equal sign in your null hypothesis, and that you have the appropriate sign in your alternative hypothesis. If you're struggling, then just do a not equal to. Right? It's better than picking the wrong sign, right? But then follow through with that not equal to, because it's always safer. Step 2, do the test, which really means calculate the test statistic. But I like do the test. Right? Figure out how far is p hat from p naught, right? And on your formula sheet, you have z is p hat minus p naught over the square root of p naught q naught over n. Now, we can plug in our values. Z is, we've already determined our p hat is 0.85 minus 0.8. How far is it from our hypothesized value? Taking into account the spread, 0.8 times 0.2 divided by 670 our n was, I think. Yeah. Okay. 0.85 minus 0.8. Well, I shouldn't have done that first. 0.05. 0.8 times 0.2 divided by 670. Don't forget that square root. Otherwise, it'll make a real mess. 0.01545334819. So I find a Z of 3.2, oops, 355447776. Yeah, sorry.
I'll just the one where
I'll use.
Yeah, in the 0.80 times 0.20, where did you get those numbers from?
Okay, so this is my P naught.
Yeah.
And my P naught is going to be the thing I want to compare my sample proportion to. And on your formula sheet, it just says generically P is equal to P naught. Right?
And then you got the 20 from the G, like 1 minus 0.2.
Yeah. Q naught is 1 minus P naught, which is 0.2. You got it. So we used the t-table last day, right? To find the p-value, because now I have my Z. And the reason I bring it up is because depending on if I want to use my Z table or my t-table, and you're welcome to use whichever one you'd like. I will tend to use the t-table because that's how we're going to do it for chapter 7. And so it's just nice to be consistent. But I'll show you now how you could use the Z table if you wanted to. So for the T table, I need 3 decimal places at least. Or maybe I don't need to do any rounding. Let's step 3. Let's just leave it there. So there, I've calculated my test statistic, which tells me that 0.85 is 3.2355 standard errors above 0.8. It's quite far from 0.8. But to quantify that, we use a p-value instead. So find the p-value. Using the T table. Let me grab this. Oops. This is where it becomes important to keep track of, okay, I've calculated a Z, and so it can go on this Z star line, right? These Zs are just Zs. Now I need to remember, do I have a one-sided p-value or a two-sided p-value? And this feels like so long ago at this point, right? And so that's why I always make a note to myself here that this is a one-sided test. So that means I need a one-sided p-value, right? And it's because I'm only concerned with one of the extremes. And so in this scenario, I need a one-sided p-value. So what we do is we take our Z, we take the absolute value of it. And so how we write that is I put it in the center of the page. Z is equal to 3.2355. Let's just lob it off there. So I'm going to take this, the absolute value just drops the negative if there was one, there isn't, so we can ignore that. But you always write it, right, just for consistency. And what we're going to find is that it's going to be between 2 values, right? So we start at 0 and then we move our way out, and we're almost out of hope until we get here. And finally, we're here. It would fall between these 2 values, right? And last day we did see the important special case where we're kind of off the table, right? Next stop is infinity. There in one of the tails is 0 at infinity, and in 2 of the tails is still 0, right? But now we're between these 2 values. And so I'm gonna need another page. So Z is between 3.091 and 3.291. So close. Which means our p-value, now as long as you remember to read it from right to left, because as my Zs are increasing, my area in the tail, which is my p-value, is decreasing, right? Then you can use the same structure. Right, and so then my one-sided p-value is going to be between 0.0005 and 0.001. You could also use Excel, right, to get an exact p-value, right, an exact area in the tail. And this is a positive Z, and so then you would need to be in the upper tail, right? Do a little bit of work for that. Alternatively, and like I said, I'm going to stick to this version because that's how we're going to do it kind of from here on out. And so, but alternatively, we could use the Z table. Maybe I'll put it on its own page here. All right. What we found is we found a Z of 3.2, let's say 4, because the Z table needs 2 decimal places. And so we round to 2 decimal places. Now, our one-sided p-value is this area in the tail. One-sided p-value. So using the Z table, right, we can find the area to the left of 3.24, right? The table only gives us the area to the left, but then we can find the area to the right, which is the one we want. So using the Z table, we find the area to the left of Z equal to 3.24 is, let's see, back in the Z table, it's been a while. 3.2, let's highlight that row. 3.24. I find 0.0 or 0.9994, no 0, is 0.9994. Which means the area to the right is 1 minus 0.9994, which is 0.0006. Very, very small. Let's check in. Is 0.0006 between 0.0005 and 0.001? It is. So here, notice that this, right, is between 0.0005 and 0.001. All of those are really small, right? And what's the rule, right? If the p-value is small enough, then you reject H naught. So our conclusion, doesn't matter how you got your p-value, whether it was software or the Z table or the T table, the conclusion stays the same. We have a really small p-value. And so step 4, our conclusion has 3 parts. Right? First, and I'm going to stick with this version of the p-value, right? Because that's the one that I'm going to be working with. Since we need to compare that to our alpha level. Now, we were not given an alpha level, but we're going to use 0.05, right? That's our default. So since our, and this is where you want to show off all the things that you have already had to tackle, right? You know it's a one-sided p-value, so why not say that? Since our one-sided p-value, you know what it's between, is between 0.0005 and 0.001, and it's less than our alpha level of 0.05. It is less than, oops, than, hey, it's glitchy. Alpha equals 0.05. Which means we have enough evidence to reject H naught. which means we have enough evidence to reject H naught. And if I'm rejecting H naught, I like to offer up the alternative, right, in favor of, but you don't have to. So compare your p-value to your alpha level. That's the first part. Then what's your conclusion? Do you have enough evidence to reject H naught, or do you not have enough evidence to reject H naught? And then finally, the one people love to forget is the conclusion in terms of the question. Do these data provide convincing evidence that more than, let's see here, hey, come on. Therefore, these data provide convincing evidence that more than 80% of Americans have good intuition about experimental design, period. Long, but not hard. And then you did it, but also time for my favorite. How do you know what conclusion? Right? If the p-value is small enough, you have enough evidence to reject H naught, the p is low, then the null hypothesis must go. Pretty fun. The null hypothesis. They did the same thing. I'll leave this for you to practice on your own. I think I gave you the answer. And then the recap. And with that, I release you.
Oh my gosh, I feel like I learned a lot today.
Nice. That's great. We did a lot.
And it's Friday.
It's Friday, party time. All right.